down that list of stuff that, perhaps, Lizion, can you switch on the light? Yeah, thanks. So I'm trying to go down to this list of topics that was outlined in the beginning, and I think we have three things missing. One is sort of like how to generate pulses in general, okay, for any of these objects, and that's what I'm going to cover today. And the other one would be spectroscopy. The Doppler-free spectroscopy we have already, is it? Did we have this? So we have this already, and then superconducting. Business is still left. Oh, superconductor and eventually high voltage, playing with high voltages. I guess that these are sort of like the topics that are on my to-do list. Okay. So today I wanted essentially cover pulse generation, or and why pulses are actually necessary. And this may be something that you may or may not have seen before, but the whole rationale of talking about quantum control technology is because you want to control quantum systems somehow. Okay, and the most common way of controlling quantum systems is shine light at them, atomic systems or color centers, or shine radio frequencies of them to change the state from a qubit in from 0 to 1, or to these superpositions of zeros and ones that form the basis of this whole quantum information science. Okay, and what I first want to do is perhaps a quick recap for the nomenclature of this two-level system, or playing with two-level systems. I probably have to apologize to those who have seen this before in atomic physics or quantum mechanics 2 or 3 or whatever, or any quantum info course. It's always the same, but it's sort of useful to keep the nomenclature sort of present. The funny thing is, it's fairly independent of which physical system you're looking at. So any of the known systems can be treated in the same way. And usually your starting point is you have a two-level system, okay, of say an atom or two states of a superconductor or two orientations of a nuclear magnetic moment in some external field. Let's just call them ground state and excited state. And I draw them vertically separated to follow the tradition in atomic physics, where you sort of like have some sort of energy scale in the vertical axis. But it doesn't need to be. Okay, it can be just any system that has stable states. And you try to transfer a quantum system from a ground state to an excited state by shining in typically some resonant radiation. Okay, so. Whenever you write down how such a system evolves, I think in quantum information science you go further and further away, at least on the theoretical part, to use Hamiltonians, because they find Hamiltonians uncool, because all they care is a sort of like an operator that transforms a state from one computational state to another computational state. So more like evolution operators are more important. But if you work with real physical systems, then typically you have to consider Hamilton operator, because you look at the temporal evolution of a real physical system. Okay. In this case, you would sort of like write down a Hamilton operator in a very simple 2x2 fashion. You have an energy for get this calculation right, of the ground state and energy of the excited state. Okay. This is a notation that writes the state vector of this single qubit as a vector with two entries. Okay, so you have ground state would be 1, 0, and excited state would be 0, 1 in this simple. So this vector would be ground state 1, 0, and this one would be 0, 1. Okay, just for the nomenclature. Then if you so a common way of describing such systems that are driven by a perturbation. So this system alone is a Hamilton operator that's written down there is relatively boring. Okay, so because it just means that this state and these states are energy eigenstates, which means they survive for long enough time to be worth being talked about. Okay, so in particular, if it's energy eigenstates, they live basically forever. Okay, so that's the definition, I guess, of an energy eigenstate. not division, but a consequence. And what you need to do in order to transfer now states between zero from ground state to excited state, or the other way around, or make superpositions, is you need to have some sort of coupling. Okay, and that is formed by typically by this radiation you shine in, and in the many cases you get a coupling Hamiltonian, okay, an interaction Hamiltonian, that is some sort of an external quantity, like a radiation here, like an electric field, times the dipole moment or dipole operator of the atom. Okay, or it could be a magnetic field. Okay, and multiplied with a dipole moment, magnetic dipole moment of this particular system. Okay, so these are typically ways how you couple to a system. Your electrical field times electrical dipole, magnetic field times your magnetic dipole, and if you're fancy higher order interactions, you can just choose whatever Hamiltonian you have that allows an external manipulation handle to change these internal states. For superconductors, it would probably be something like that here. Okay, so if you have a superconductor, you can also shine in radiation, change the state from one orientation of the flux to another flux orientation. You just need to figure out what is your controlling field to change a state from this one to that one. Depends on the physical system. Okay, so far so straightforward. Usually these so when I write it like that, then these fields here are externally driven fields. Okay, so this would be, for example, a light field. You shine onto some microscopic dipole, molecule, atom, ion, whatever. Okay, and this operator is acting on that space of your microscopic system. Okay, so and what sort of like, just to set the nomenclature, what you typically have is an external perturbation that corresponds to an oscillation at a frequency that bridges the energy difference of these two levels. Okay, for example, you have in ground in the excited state, and the energy difference is E excited minus E ground. Then you need to drive, or you can excite the system by driving it with a radiation where the frequency times h bar is or times h is just the energy difference between these levels. I mean, it's like just rephrasing what you know already. So typically, you have, and I just stick with the electric field, but the exactly same holds for magnetic fields. Okay, you have an electric field that's your external quantity. Okay, E naught times sine omega t. Okay, and you choose that this omega minus excited state energy, ground state energy divided h bar is approximately 0. Okay, which means that you try to drive your system nearly in resonance. Okay, so this is sort of like, if you want, this is sort of like I'll just call this a detuning of a sine wave you send onto this object. Okay, so yes. Now what you then do in order to see what is this system doing under the radiation you shine onto it is you do a so-called rotating wave approximation. Okay. Because you have a situation where this interaction Hamiltonian here now becomes time dependent through the external field you drive. Okay, so that's a bit of a messy situation. You usually would like to write down the equation of motion for that state. Okay, equation of motion is I h bar d dt. State is h state. Okay, and this h now is the sum of the unperturbed Hamiltonian, okay, and the interaction Hamiltonian. And that thing becomes time dependent, so this gets a bit of a messy differential equation. Okay, And the standard way of solving this is so-called this rotating wave approximation, where you essentially, I mean, not going through the details because that you find in all depth and detail explained either in quantum physics books or in atomic physics books. So that you just find nicely written down there. You get an effective Hamiltonian, or effective interaction Hamiltonian that looks like h bar over 2. So minus delta omega r plus delta. Okay, that's sort of a short version that, you know, so you try to get rid of this basic Hamiltonian, the unperturbed Hamiltonian, and try to include a contribution that is given by this electric field. Maybe I should be one step more detailed. I guess this dipole operator typically populates the off-diagonal elements of your Hamiltonian. Okay, so I would just write this just for the upper part would be 0, so it doesn't contribute something to the energy typically. Okay, and or you know, in some approximation, and then you have electric field times dipole moment. Okay, or actually the whatever ground state, dipole moment, excited state, and here excited state, dipole moment, ground state times electric field. Okay, this is sort of like the way how this Hamiltonian looks like. Okay, so you have the expectation value of the electric dipole moment for an atom. If you have this coupling of the atom times the electric field. Okay, so this is how this interaction Hamiltonian look like, and what you're left with is sort of if you combine these two things and you know, do some approximation, then you end up with a effective Hamiltonian that combines the ground and excited state into something that looks like this friend here. And there's a definition that's this sort of like off-diagonal element that would be so-called Rabi frequency. Okay, this would be this d times E or mu times the magnetic field. Okay, divided times h bar, I guess. Okay, and this thing is called Rabi frequency. Or actually more Bayer Rabi frequency. Okay, Bayer Rabi frequency, because that essentially expresses how big is the electric field. Okay, or the you know, the energy in you know, of the. Well, I should write here E0, okay, because I have here the field amplitude E0. Okay, so this is the field amplitude, the electric dipole moment, and I then get a Rabi frequency here. Now, the tuning I have introduced already. The electric field I have written down there. So this becomes a relatively simple problem to solve. Okay, so one thing to keep in mind is you just for clarifying language. Sometimes people say, oh, this is an X operator or Z operator. Okay, so you can write this Hamiltonian also in form of the Pauli matrices, h bar delta over 2. Okay, so that gives the diagonal part, and this would be sigma z. Okay, for those who like to use Pauli matrices to describe things. And sigma z is this. Sigma z is, if I hope I don't get it wrong, +1 -1 0 0. Okay, plus, and then there's one. I think that's typically referred to sigma x, omega r over 2 times sigma x. Okay, and sigma x is. Hope I get it right. Okay, so this is just to when you run into this definition, you can write this interaction Hamiltonian in various ways, or you also the original Hamiltonian in a particular way. But especially in NMR, it's very common to call something an X or Z interaction. Okay, In this simple case, it would be on the Z or on the diagonal part. You would just see a detuning of the driving field from the unperturbed resonance. Okay. Okay. So now, if you work with this system, you have you can simply come up with the eigen energies and the eigenvalues. Okay, eigen. Okay, so the eigenvalues of this Hamilton operator, lambda plus minus. I mean, it's a two-dimensional system, so you expect two eigenvalues are plus minus h bar omega, h bar over 2 square root of delta squared plus omega 0. Oh, is this the same omega Rabi here? Omega Rabi, okay. Squared. And that is sometimes written as plus minus h bar omega effective Rabi over 2. Okay, so yeah, maybe just call this here omega effective. Okay. Whereas this omega r is the Bayer Rabi frequency. Okay, and this combination here is the let me just draw this correct. Okay, so this is the effective Rabi frequency. Now, why is this an important frequency? Now, if you switch off the tuning and you're driving your system on resonance, meaning that delta is 0. Okay. You can look at the solutions of this of the population of the ground and excited state and say if you start the system being in the ground state, okay, and you switch on this interaction, then this is not an energy eigenstate anymore, so it will evolve over time, and it will evolve from a ground state to a different state, to an excited state, and come down to a ground state, and it will just oscillate sinusoidally between ground and excited state. So what I draw here is, say, the population of a particular state, and this would be the population, see, of the ground state, and correspondingly, you would see a population of the, am I making a mistake here? Hopefully not ground state. Oh, this would probably be the excited state, okay. If you start in the ground state, then the population of the excited state is 0. The population of the ground state is 1, okay. And the other one is just the opposite here, okay. So this would be a population of the ground state, okay. And the overall population adds up to 1, and this is sort of like the basic behavior of such a system. If you start in a ground state, then it just oscillates. This period here, okay, from here to here, period, and that sort of like period 2 pi is the period over this Rabi frequency, or this omega 0 here. Okay, so this effect here, and you oscillate between ground and excited state, is called a Rabi oscillation. Okay, so this whole thing, Rabi oscillation. Okay, and that essentially, okay, so this is what happens if you're on resonance. If you happen to be not on resonance, okay, then just see whether I get this right here. You get a similar behavior. It's just this time you, if you look at the population of the excited state, you don't get completely into excited state, okay, but you stay sort of like, oscillate to some level, okay, and then come down to 0 again. And for the ground state, you just do the opposite. Now this is a horrible drawing, okay, but I guess you know what I mean here, okay. Now this oscillation is faster, okay, and the amplitude is smaller, and the period here, okay, this would be now, I'm not sure whether it's readable, okay, this prime would be 2 pi over this effective Rabi frequency, okay, and that's this expression given here. So if you increase the detuning, it will oscillate faster and the amplitude will get smaller. That's just a consequence of if you do the diagonalization and work out how the state's going to evolve in time. It's really, I'm not going into this because you should have seen this in either atomic physics or quantum mechanics or quantum optics or quantum info or anything. There's sort of a nice way of writing. So far I think I just gave the eigenenergies, okay? The eigenstates I also have to write down. Okay, corresponding to this value plus and minus, okay, plus minus, okay. They can be written as, with the same nomenclature here. I hope I get this right here, delta plus minus omega effective times ground state plus omega r excited state, okay, and then normalization factor to keep the whole state normalized, and that's, well, square of these two guys, delta plus minus effective squared plus omega Rabi squared. I think that's the expression. Now this looks reasonably messy, but just to make a connection, what you may have seen in other ways of dealing with two-level systems, you can write this as a mixing between ground and excited state. Okay. So if you just write this down here, plus would be cosine theta over 2 ground state plus sine theta over 2 excited state, okay? And the minus state would be just the other part of the rotation, sine theta over 2 ground state, yeah, okay. Minus sine, okay, plus cos theta over 2 excited state. That you may have seen in things like neutrino oscillations, or when one neutrino moves to the other one. So basically you rotate in that particular space. You have a particular coupling. I guess in this this sort of like driven two-level system scenario, you would call, this thing has a name, okay, so this relationship tangent delta. It's just simply omega Rabi over delta, okay? Where you have to choose a way of defining delta, so this delta should be in the interval of 0 and pi. Okay, just to make sure you choose the right definition of tangent. You can do this in many ways. Okay. And that thing, I guess, I have seen it being labeled as a Stückelberg. But I'm sure there's enough theorists in various places that claim that this is their toy. But this is basically just a mixing angle that tells you which eigenstate has how much ground and excited state contributions. So it's a very convenient way to write this. Okay. So yeah, because before we go now to that, so here you should already get an idea that that in order to get from one state to another state, you could just use or expose this atom for a given time by an amount of light field, and you don't just randomly excite atom like you would do shining light in the spectroscopy cell or something like that we sort of we're only dealing with populations. I mean, we haven't gone through the detail, I guess, but here you can actually bring the an ensemble of quantum systems completely in excited state. And this is what you really want to do, or from ground to excited state, or even funnier, to bring it from, so, I mean, basically, if you have this evolution going on for half a period, okay, then you just flip ground and excited state, okay. So this would be a pi pulse, okay, so this is changing states. Okay. And what you would do is you take, you change your Rabi frequency or the electric field amplitude via this relationship here. You just switch on your electric field or the optical field or magnetic field that you have for a given amount of time. Okay, zips, such that the populations for the excited state, let me just try to get this drawn correctly. Okay, move for the ground. So ground state. Okay, if you have your interaction in the beginning completely switched off, then your system is not in the excited state. The population of the excited state is 0. The population of the ground state is 1. Okay, so this is when the interaction is off. Just your ground state is in the ground state, excited state is in the ground state. They just move on in time. And when you now switch on this interaction, then you just follow this dynamics that's shown here. And here we just get this oscillation just down to the ground state here. Okay, and to the excited state here. Okay, and then you switch your interaction off again. The color's wrong. Okay, and that basically have swapped these populations. Okay, this time here, okay, is just chosen. Okay, that you just get pi divided by omega. I hope this is right. Divided by omega Rabi. Okay, and this is assuming that delta is 0. Okay. So this pulse of transfer that does exactly half of a Rabi oscillation is called a pi pulse. Okay, and that you can then write down a time evolution operator for a system. Okay, and it's just an inversion. So it would be ground goes to excited, and excited goes to ground state. Okay. So this is called a pi pulse. Okay, and now the funny part is not just build an inverter for these two-level systems, but it can also make these funny superpositions. Okay, then you do exactly the same game as before. Okay, but this time you have a Rabi frequency. Okay, they switch on say for half of this time. Can you switch it off again? This should be time, okay. And then the population of the different states, this would be rho. We started out in the ground state, so excited state was 0. And then this would be the ground state population, rho ground, okay. And if you just do the same thing here, so initially everything is in ground state, okay. And then from that period on, it just goes zips halfway down, okay. This is maybe not so the nicest thing. And then continues. And I just try to draw this here. And for the excited state, you first have nothing in the excited state, and this goes then here, and then it ends up in half of the population being in the excited state. But this state here is really just a linear superposition of ground and excited state. Okay, so I just don't write the phase factor, but just the population, rho. Excited, and then this was the rho ground, and rho ground, okay. So this was for the situation with a pi pulse, and as no big surprise, this is the so-called pi over 2 pulse. And the reason for that is because this time here, okay, t prime is just pi over 2 divided by Rabi frequency. Okay. So these are the basic tools how you do a simple qubit manipulation with atoms or nuclear spins or qubits and whatnot. So that's the basic processes that you use when you talk about simple quantum control of quantum systems. Okay. And that's sort of like the easiest way to transform or bring a population from one to the other state. Now, what you realize when you do that, you need to get a few things right. Okay, one is you always have this requirement that the tuning is 0. Okay, so you really need to match the oscillation frequency of your driving field, this one here, okay, to your atomic resonance. And the question is, how precise do you need to match it? And that's simply within a fraction of the line width. Okay, I'll just have I? Yeah. Okay. So I should probably give a little bit more information how this relates to practical system. But you need to get this so the laser frequency or magnetic field frequency, relative close to the transition you're driving. Now, the next, well, I'm just talking rubbish here. It's not the line width, but anyway. So you need to control the detuning. Then you need to also keep the field amplitude constant. Okay, or you have to have that pretty well under control. This omega Rabi, okay, is essentially proportional to the light field amplitude or electric field amplitude, okay, or magnetic field amplitude if you have a different coupling. So you need to keep the amplitude fairly stable, just in order to be sure that you really get a pi pulse or pi over 2 pulse. Okay, otherwise you end up not all population being transferred, okay, or the timing is not correct. So amplitude needs to be correct, detuning needs to be 0, and the time needs to be quite well controlled. And these are the experimental parameters you need to control, okay, in order to do these pi pulses. So there's one more thing that they can do that's worth mentioning, since we just have this formalism on the wall here. You can also try to do adiabatic transfers. Okay, in order to bring something from the ground state to the excited state, you can either use a pi pulse or an adiabatic transfer. Adiabatic transfers means that you always stay in an energy eigenstate. Okay, so you change something in the system, but you always try to stay in so you change something in the system, like the light intensity or the tuning as a function of time, but you do it slow enough such that the system likes to stay in an energy eigenstate. There's something like the instantaneous energy eigenstate. Okay, is a silly word, because now what we have is so okay, other trick. Okay, make H interaction effective. That's time dependent. Time. Okay, I mean it's written here in a non-trivial way. Okay, so far what we have used is we got rid of the time dependency from the oscillation, okay, of the electric field by this rotating wave approximation, and there I refer you to either atomic physics or quantum physics. Okay, so this does not contain explicit time dependency. Now we make things and this pi pulse thing here. Okay. I basically, this is not time dependent here. This is not time dependent. It's just sort of like a transition to a different set of fixed Hamiltonians. Okay. Now what you can do is make these things explicitly time dependent. Okay. And then there's something like for each point in time, where you, for example, vary the Rabi frequency or detuning, there's an instantaneous energy eigenvalue or instantaneous eigenstate of this Hamiltonian. It's not an energy eigenstate anymore, because obviously you have a time dependent thing, so it cannot be energy eigenstates are defined by having a particular behavior in time. So if you make this whole thing time dependent, it becomes a complete mess. But it still makes sense to look at such states, and I'll just give one example. Okay, where you have, let's see whether I get this right here. So you have a time, and say you vary the Rabi frequency, say by some funny envelope in time. Okay, so you make light on and switch it off. Okay, and maybe you change also the detuning here. Okay, detuning as a function of time, and that you just change linearly. So at t equals 0, you have no detuning. Okay, and at larger times, so you just have a linear increase of the detuning. This would be called a chirp. For obvious reasons, because you go from a low frequency to high frequency for the light field. Okay, whoop, something like that. Okay, so you switch on the electric field or on and off in this particular way. Now, in order to figure out what's going on, you can draw the instantaneous eigenvalues of the system. Okay, so lambda plus minus. Okay, plus minus. Okay, as a function of time, and you would get okay. Is this obvious to see here? So, okay, if we go to detuning 0, then we would have the detuning 0 would mean we have this plus minus states are ground plus excited and ground minus excited. Okay, so detuning 0 would be in this case here. Okay, we have the plus state, and here minus state. Okay. They're just, 1 over square root of 2, 1 plus the other, or 1 minus the other. If you go for extreme detunings, or when the intensity is almost 0, then you would. So basically, you can sort of like work out in this scenario what is the instantaneous energy eigenvalue, okay, or pseudo energy eigenvalue, I should say, okay, and then you get sort of like a trace that looks like that. Okay, I'm not sure whether I get this right here. Something like that, okay? And these the fact that the distance between them grows faster, larger and larger for large times or not very large times or very small times, it's just owed to the fact that you get, where is it? Basically on this diagonal element, you have this detuning here. This is still the effective Hamiltonian in this rotating wave approximation, okay? But to make the long story short, these states here asymptotically would correspond to, say, ground state here, okay, an excited state here, and for the other detuning, you would have a ground state here and an excited state here. Okay, so now the trick of an adiabatic transfer is you change these parameters slow enough that if a system is either in the ground state or excited state, okay, it always likes to stay in these local energy eigenstate. If you change it slow enough, then you won't find transitions to the other branch. Okay, you just adiabatically follow that curve here, and you adiabatically transform from ground state to an excited state. Okay, or from an excited state to a ground state. Now that's a super useful technique because now the rate of transitions from one branch to the other branch, these are called I guess Landau-Zener transitions. If this doesn't look like that, but you have a nice hyperbola, you can actually work out how big is the transfer rate if you move through this system at a particular speed. That gives you an idea how fast you can apply these fields. Okay. In such a scenario, it's a bit messy, and I would say don't bother, just simulate it numerically, you see what you get. Either this equation or, yeah, it's probably good enough to do the effective Hamiltonian. Yes?
Sorry, but so on the y-axis here, I don't understand how the ground state would be higher in energy than the excited state in the shoe.
Because we changed the detuning. We are now looking at the eigenvalues, okay, of this effective Hamiltonian here.
Yes.
Okay. And I have sort of like an upper, what sort of corresponds to the effective ground state and the effective excited state, okay? And I have a plus delta here, the minus delta over 2 here, okay? And if I flip the sign, okay, then you just the ground state, changes the sign of its effective eigenenergy. That's all. You just, maybe just rushing through this too fast. If you look at for a scenario where delta is positive, okay, and omega goes to 0, then you can figure out which of these two branches corresponds to ground state and which is the excited state. So Rabi goes to 0. So tangent, is this sensible? So if you restrict the tangent between 0 and pi, then you yeah, it's a bit of you basically, this ratio is slightly positive or slightly negative, and it will correspond to either 0 or pi, okay, for this angle here. And that means that if you have 0, then the ground state is plus state. If you have pi, then the excited state is a plus state. I'm not sure whether I'm making this clear.
I think it should make sense.
This is maybe, I think this is a bit of a silly definition of tangent because it goes through what's it called, a pole here. You can define the whole thing as a cotangent of the whole thing and then take the other ratio and then, so I guess you could also write cot is delta over omega r, and then you don't get this discontinuity. But that's, anyway, so this is all the standard gymnastics that you have to go through if you play with two-level systems, okay? And I would recommend, if you haven't seen this before, just look it up because that is the basis of all this, change of states of quantum systems. Most important thing you probably would hit this, pi pulses, pi over 2 pulses, pi over something pulses. Okay, this is basically driving a Rabi oscillation for a fraction of that oscillation period. But you can play funny tricks with adiabatic transfers as well. This is just an example. It's also reasonably important to know that how to deal with such a scenario. Simply because when I draw a pulse that looks like a square thing, okay, like switching on the light instantaneously and then it's on and then you switch it off, may be practically not that straightforward. Okay, so you may find a situation that you have to ramp up the intensity with a particular profile. In all practical systems you will have to do this. You want to understand, is this affecting your transfer? Okay. So then, I mean, you can work out basically if you're on resonance, what's the integral over this curve to make sure that you have a pi pulse. But that's just something you have maybe to play with on this 2x2 Hamiltonian. This is also why it's useful if you want to do a simulation in a practical system. Get to learn how to do a simulation of your Schrödinger equation with the profiles you have. Okay. So then you can, whenever you do an experiment, you may not have such a situation, but some funny other aspects of your envelope or your detuning. Learn how to solve this equation here, the Schrödinger equation here, for whatever system you have. And if you want to do this, or if you want to figure out, how fast can I drive a system, or how strong do I need to have my light field in order to get a particular Rabi frequency? Okay. You also need to work out the connection between electric fields and frequencies. So just show where I just write this down here. Connection of omega r to E0. Okay. The first thing is if you work with real light, okay, so you have electric field strength, okay, is just given by 2 times the intensity, or electric field amplitude, intensity divided by, I think, epsilon naught c. Okay, this was an intensity. That is what you find, for example, in your Gaussian beam of some sort, okay? So you have a laser beam, we're dealing with laser beams, okay? You can work out your atom is sitting in this laser beam somewhere, okay? The laser beam has a particular geometry, say a beam waist or so, that allows you to calculate what's the intensity at the location of your microscopic system. Then you can work out what's the electric field at the location of the atom to drive this thing, okay? So this gives you this field amplitude. Typically the electric dipole moment you may or may not find quoted in some funny units. Intensity is watt per square meter. Okay, this would be here volts per meter. What you typically have is the atomic system characterized. Is characterized by sort of like a decay time. Okay, so if you have a coupling from the excited state to ground state in an electromagnetic field, then you, I mean, all we deal with here is a field that's not quantized. Okay, so this whole mechanism, you don't need to quantize the field. That said, okay, if you have a coupling to a classical electric field, you can also quantize that field, and then you will find transitions from the excited state to ground state even in the absence of a driving field. Okay, it's called a spontaneous emission. So that's just a consequence of the fact that you couple to an electric field, and you have to quantize the field, leads to spontaneous emission. Okay, so whenever there's a dipole coupling between the excited state and the ground state, you do have spontaneous emission, and there's a spontaneous emission rate, gamma spontaneous, from excited state to ground state. Not sure the camera can read this. Okay, so that's what you have. Okay, what's the inverse lifetime of the excited state? Okay, if you want, you can make this connection between this gamma and the dipole moment. Okay, and this you can work. This is really atomic physics. Okay, 3 pi epsilon 0 omega naught to the cubed divided by h bar c to the cubed times electric dipole moment squared. So that's sort of like a way to get a connection between the dipole moment and the decay rate. Okay, and if we just recall, so practically, I mean, you can work out these numbers and make a 50 million mistakes for science and orders of magnitude, which typically happens. But what you often do is you realize, okay, electric field is proportional to the square root of the intensity of your light beam. Okay, and the Rabi frequency is proportional to the electric field amplitude. Okay, so you try to express this Rabi frequency as a function of the intensity. Okay. Intensity of your light field, and then sort of a convenient way of characterizing the intensity of a light field is the so-called saturation intensity. So, and that is intensity where you drive a quarter, the population from the ground state to the excited state, not to half, but a quarter. Okay, so you get sort of like a balance between spontaneous decay and excitation. Okay, and that intensity is called a saturation intensity. That came up not explicitly or quantitatively in this laser spectroscopy part, but if you were to calculate the line profiles, quantitatively, then this would be a useful quantity. So, I saturation, okay, and for no good reason that's sort of like a factor of 2 here, and then you would need to sort of like transform this scaled intensity into something that has a unit of frequency, and then you just get this spontaneous decay rate here. So that's a relatively simple definition of this. If you want a definition of the saturation intensity, okay, and the connection you have, I is saturation intensity is gamma times omega naught to the cubed c cubed h bar c over 12 pi. Or if you like to get a simpler expression, it's pi hc over 3 lambda cubed times the inverse lifetime here, or the lifetime of the excited state. Okay, so these are, if you have any transition where you know the lifetime, then you can figure out what's the intensity, what's the saturation intensity, and what intensity you need to get a particular Rabi frequency. These are the decisions you need to make if you want to drive a system. Okay, you somehow know typically what's the decay time. Okay, then you can work out how strong of a field do I need to play these games here. Another important consideration is, in order to figure out how fast do I need to make this transition here. Okay, so as you see here, in this quasi-classical driving field scenario, there's no decay. Okay, so that's just an oscillation, and this would continue forever between the ground and the excited state, simply because we treated the field here classically. In this description here, we silently sneaked in things like a spontaneous decay rate, simply because it's connected to the dipole moment of your system you're driving. Okay. You typically want to have your Rabi transitions being shorter as the natural decay time. If you work with a grounded excited state. The other smart thing to do would be not to work with grounded excited state, but to degenerate or mostly degenerate ground states and avoid any coupling. Okay, then this trick here still works out. So you could for example use a very popular system is something like that. You call this state 0, okay, and this state 1, and these may be two magnetic sublevels or vibration states of some sort. Okay, and then you couple. You basically switch on some sort of a coupling by using an intermediate state, okay? That's maybe somewhere here, okay? And transferring excitation from here to there by going through an intermediate state. Okay? That thing would be called a Raman transition, okay? That's all atomic physics business, okay? But then you can sort of like, between these two states, you can work out exactly the same effective Hamiltonian and do Rabi oscillations between these two states. Okay, so whether you use a direct optical transition or an indirect optical transition through a Raman transition here, okay, doesn't matter. It's always the same mathematical formalism. Okay, I guess that's what. Just trying to see what I'm doing time-wise. Okay. Now we would come to the more practical part, okay? So you have sort of like the toolbox there to figure out how long do I need to make my pulses, okay? How strong of a light field do I want to use for something? Do I do a pi pulse or some funny chirped transfer? And now the trick becomes, okay, how do you actually modulate your light fields? And I guess we have covered some of that in the electro-optic modulator section or the acousto-optic modulator section, where we just said, you can switch on and off a light field or change the phase of a light field electrically. Okay, but maybe I should have a quick stop here. Are there any questions so far? Because I'm going to erase this and yes? Yes?
Does it suggest you never switch off your chirp field?
You do. So if you look at this diagram here, so you have a detuning and an amplitude. Okay. So what I could do for this particular scenario is write down your electric field as a function of time, how this would look like. Okay. So let's just do this because we can. Okay. So electric field for this thing here, okay, as a function of time. Now I would, in this case, you have a detuning 0, and I have a maximum amplitude, okay. So I just try to let's choose some frequency, okay. Usually the oscillation frequency of the driving field is much faster than the transit time here. So I would just draw some oscillation, okay. This should be symmetric. Okay, let me just try to do this. Time axis comes later. Okay, so I have an oscillation of some frequency here. Okay, maybe a few oscillations here in the center. Okay, if I go to the outside, okay, this Rabi frequency would be something like the amplitude. So I have an envelope, okay, of my oscillation. That looks like that. Okay, so my oscillation needs to stay within there, and it will go to 0 at some point, and will go to on both ends. So before the pulse and after the pulse, it will go to 0. Yeah. I mean, at some point, the tuning becomes pointless because you have no electric field. Okay, but in this case here, the tuning would be negative. Okay, so it would be sort of like a slow oscillation. Okay, at some point, look something like that. Okay, or maybe it goes slower and then something like that. Okay, and then on the high side, the oscillation goes faster and faster. Something like that. Okay, as a function of time here. So it goes whoop. I'm sure you can. I cannot vocally make this thing, but okay. So you get the picture, and maybe you can program it and see how this whoop goes. And that would drive the atom sort of like from ground to the excited state or the other way around. And again, it's a trick that works also for Raman transitions. Okay. So you can play exactly the same game because you have an effective Hamiltonian that looks like that. Whenever you have something like that, you can play such games. Yes.
We once had a visitor here from Rainer Blatt's group.
Yeah.
Who was talking about suppressing spontaneous emission by building a spherical cavity in which the is placed.
Yes.
And in your equation, I don't see how that would affect the spontaneous emission.
Okay, here we don't play with the boundary conditions. This thing here is just free space. No funny boundary conditions whatsoever. You have one atom sitting there in free space. The thing can decay wherever you want to. That's the most typical scenario. Now, if you start to look into what effects do funny boundary conditions have on the electromagnetic field for your spontaneous emission, it will change these expressions. But what you do there is you play with the boundary conditions of the electromagnetic field. Then you can do all kind of things. Typically, you need to work with cavities, because I mean the standard description is you have free space and infinite extent. Okay, that's the standard description of how to work with electromagnetic field and how to explain spontaneous emission. If you introduce funny boundary conditions in form of cavity, then you have the electric field at various parts of the cavity changes. Okay. And this is exactly the electric field that drives transitions. So you may have your atom sitting somewhere where there's no electric field in the eigenmodes of that thing. And then you just kill transitions, full stop, no spontaneous emission.
There's one they built this cavity and tried to tune it precisely to this transition frequency between the ground and the excited state.
Yes.
And they had problems tuning the cavity. And
yes.
they thought they wanted to apply, I think, temperature or something to just control the
okay.
expansion. So based on this, just making sure the Rabi frequency cannot affect the transition frequency between the ground and the excited state here.
So what that game does, okay, is whenever you have a different set of boundary conditions, you play with a spatial dependency of your electric field. Because, I mean, the atom is sitting somewhere, okay? And it has some position, and the position uncertainty of this thing is typically small. Okay, the thing is maybe 0.1 nanometer large, okay? And the relevant length scales for your electric field to change in that set of boundary conditions is something on the order of a wavelength, say a few hundred nanometer or micrometer or whatever, okay? So, or for magnetic transitions, even millimeter or centimeter, okay? But at any point in space, for a given set of boundary conditions, you can work out what's the field amplitude of a particular mode of that field, okay? And that can be 0. Now, if you have a 0 field there, you won't drive any transitions through spontaneous emission. That's the whole trick what they're playing there.
Yeah.
You may also get stronger spontaneous emission if you go from a node, okay, to an antinode. Then the field at that location, just due to the boundary conditions, is very large, okay, and you get enhanced spontaneous emission.
I just wonder if they could, instead of focusing on tuning the cavity, they could tune the ground and excited state by modulating the intensity.
Yes. I mean, there's a million ways, okay, how you can play with this. I mean, I would say that's an atomic physics question. Typically your ground and excited state energy is in an atom is given by how the electrons talk to the core to the charged core or to each other, okay, and depending on how you want to model it, you end up at some point with an energy level spectrum that covers most of the interactions that you're interested in, okay, and then that may include coupling to a magnetic field, so you may see Zeeman shifts or static electric fields that cause a Stark shift or God knows what. Okay, anything you feel happy to apply to your atom will change these energy levels. But that's I would say outside the scope of that playing with your population transfers. That's atomic physics, okay? So if you want to learn that, go to an atomic physics course. That's. Any other questions? Yes?
Why could t take minus values? Did I miss something?
When t?
Yeah, take minus values.
The pulse time here?
I mean, in that picture.
Oh, which one here?
The curve.
This one here?
Yeah.
Oh, okay. So okay. So because I call it 0 here, time 0 is when the amplitude is largest.
Okay.
And this is just before the amplitude is largest means time is negative, and after amplitude is largest is positive.
So at the left side is where we start the experiment.
Correct. Okay. So just to give an example. Okay, here it's like 4 p.m. Okay, it's very slow change. Here's 3 p.m. and this is like 5 p.m. Okay. You just, and say the pulse happens at 4 p.m. That's before that time and after that time, and that will correspond to different signs here. This would be a very slow transition, though. So, typically, you do this. Actually, the attraction of this trick here is you can do this very fast. And the trick is you just use a relatively large intensity. Okay, so then you separate these two branches very far. You just by cranking up the Rabi Rabi frequency or the bare Rabi frequency, and then sort of like a temporal change will make it very difficult. A fast temporal change will make it still very difficult to make a transition from the one branch to the other branch. Okay, so simply by just moving these two branches far apart, okay, makes it very unlikely to go from one branch to the other branch. So you can sort of like compress the time here substantially. And that means you can use funny pulsed lasers, very short laser pulses, okay, to drive these transitions. And that has a big advantage because you can make the whole transfer process in a time that's significantly shorter than the spontaneous spontaneous decay time. So for an atom, you can do this maybe in tens of picoseconds or so, simply by just using a very strong light pulse with this particular chirp. That's sort of like the idea. I mean, these adiabatic techniques, maybe it's not so common for two-level systems, but for these systems here, where you do these Raman transitions, you bring everything from here to here in a very short time, simply by applying a very strong field. And very strong fields are not so easy to control with the exact amplitude, so these adiabatic transfers are advantageous. In many cases, like nuclear magnetic resonances, you do these type of pulses very frequently. But that's always sort of like the simplest way of doing it. Hit the resonance and apply a field for some time, and then it transfers from A to B. Yes?
When you apply the rotating wave approximation to get the effective Hamiltonian,
Yes?
it is something like we move to the Dresden picture, or
no. So the Dresden atom picture is
the diagonal term of the Hamiltonian is nothing but the detuning.
Yes. So rotating wave approximation is you basically write down how to go. It probably takes me a while to get this right. You have an e to the I omega and e to the minus I omega term you introduce, and so they basically break down this sign thing in a omega and a minus omega term, and then you can sort of like make this transition from the original states to these oscillating states. But at some point, the Hamiltonian becomes like that by just throwing away terms that oscillate with a higher frequency, like at 2 omega. That's the rotating wave approximation. So that's but I think it's just a way to get rid of this sine wave and replace it by an exponential. And then you, in order to leave the effective 2x2 matrix that simple, you just have to throw away terms that oscillate with 2 omega. That's a rotating wave approximation. Dressed atom picture means you look into the states of an atom, the internal states of an atom, modified by an energy that's being created, or effective energy that's being created by an external field. Now, you can use this Hamiltonian to provide your dressing. Okay, in that sense, this would be the dressing of your atom, but how you modify the energy levels of this original two-level system in an external field. And then I guess there's various levels of depth. You can either quantize the field or just use the classical field here. But in some sense, I guess it is addressed. I think the dressed atom picture is looking into the energy eigenstates of an atom or subset of the atomic system in an electric field. And in that sense, I guess it's the same thing. So maybe this clarifies the similarity, hopefully a bit. Any other questions? Now, what I wanted to maybe also show a little bit, but this becomes very technical, how to actually make such pulses. Okay, and so this is really a completely different story. This should sort of like motivate why you need pulses. Okay, how to choose your optical powers or magnetic field strengths. Okay, and now you need to provide a light field or a chirp or something like that. You need to actually make it. Okay, and look at various devices that can be useful for doing this. Now this is all stuff you find in a theory lecture or in a advanced atomic physics lecture, I guess. How do you go about practically making a light pulse? Okay, so we have seen these various modulation techniques. Okay, so I hope I don't need any of this anymore. I think the easiest thing to understand would be a acousto-optic modulator, where you switch on and off a sound wave. Okay, and if the sound wave is present, you scatter away light field in a particular direction. And then you can use sort of like the sound wave to switch on and off a light beam. Okay, and also change frequency if you want to play these chirp games, or you choose a particular detuning. Okay, and then the trick becomes of how can you make something that controls these acousto-optic or electro-optic modulators, or any system that you use to have your coupling field. Just try to clean this here. So practical. Okay. So one thing, we have a light source, okay, modulator, okay, and then something comes out, and what you really want to have is sort of like electrical field strength that is quiet for some time, starts to oscillate for some time, okay, and then it's quiet again, okay, and these times here depend very much on what physical system you're driving, okay, but it can be anywhere from a few nanoseconds, or even shorter sometimes, okay, to a few milliseconds. Okay, so that's a typical range of pulses you need to cover. So you could use, and sort of like what you typically do is you have your a continuous source, okay, a light source, or a radio frequency source that is resonant with this transition you want to drive, okay. You need to switch this on for a short time, and then off again, okay. So the trick is how to make your control pulse such that it creates a pi pulse or pi over 2 pulse or whatever you need. Okay. In some sense, it's a relatively boring question, because we mentioned before you can build an electronic thing that you basically have a time and you just count how many clock cycles you need to switch it on. Okay, and for a given amount of time. Okay. Okay. you have it. I mean, you have it off for some time, and then for 3 pulses, you switch it on, and then you switch it off again. So far so boring. Okay. And I'm sure you can either do this with a microcontroller, with an FPGA, and whatnot. Okay. Typically, you have all of these techniques have one thing in common. You have a certain time resolution for this technique here. You can get very fancy pulse generators. Okay, then they have a very high time resolution. But most of the time, if you control a complex system, you would probably do this in an FPGA over the microcontroller. And there, the time resolution you have is something on the order of tens of nanoseconds. Maybe some is faster, some are slower. Okay, but 10 nanoseconds. And that becomes a bit coarse. Okay, for choosing exactly what you need to do for a pi pulse. You can say maybe this is not a big problem because you can always play with the amplitude a little bit. Okay, so you can adjust your Rabi frequency more or less continuously, and then this would not be a big constraint. Okay, you may want to run into maybe in a situation where you need to make extremely short pulses. Okay, and in such a scenario, you probably have to use hardware tricks to make very short pulses. Okay, or you spend a lot of money for a fancy pulse generator. Okay, and one example would be if you need pulses that are sub 10 nanoseconds or so. Okay, one thing you could do is make a long pulse. Okay, so making short pulses. Okay, you could use a long pulse. Okay, and then sort of like combine it with a delayed version of it. Keep in mind that 10 nanoseconds or a few nanoseconds corresponds to a few tens of centimeters of light traveling through either air or an electrical signal traveling through a cable. Okay, so you will likely be in a regime, at least if you work with pulses on a nanosecond time scale, that the cable length, that the electrical pulses are maybe a few meters long in your cable. Okay, and then you can sort of like play games and say, well, you have a pulse. Okay, and then you sort of like make 2 copies of these pulses. Okay, and delay one by something. Okay, such that it arrives a bit later. Later would be, I guess, something like that. Okay, and then you just do some logical combination of these 2. Okay, and see this one, and you can say you would like to get an operation where you get a pulse out when A is on. Okay, and B is not on yet. Okay, something like that. And I'm not sure whether this is a following some notation. Okay, so basically you want to have, whenever this pulse is on, you want to get a pulse there, unless this pulse is on. Okay, then you want to have this off. Okay, so the resulting thing would be this sort of like thing is only true during that period here. Okay, so and then by playing with this delay, okay, you can force a relatively long pulse. Okay, to get a relatively short feature. Okay, so then you would end up here with a time delay or time width. Okay, that's just corresponding to this difference between that pulse and that pulse here. Okay, and then you can just do with normal cables usually. So that's as long as you have a fast enough gate. Okay, that can do this operation. You can play all kind of funny tricks with simply with cables. If you need to make short pulses, and you don't have deep pockets for a generator that has a time resolution in the sub 10 nanosecond range, then you can play with this trick here. You can also nowadays, I guess, if you program these FPGAs, that's a typical thing to use for making such pulses. If you find that the device you chose is not fast enough, you often get devices that have devices built into to make serial communication. So FPGAs, a typical timing slice is on the order of 10 nanoseconds. Simply that because that's the time it takes to go from one side of the chip to the other side of the chip is a few nanoseconds. And anything faster is difficult to implement in the standard way in FPGAs. But what you have in there often is what they call a serializer. Okay, so if you have any funny pattern with, say, 16-bit or so, okay, then they send this out at a much higher frequency than the standard clock of your FPGA. So in that sense, you can push the resolution of the timing maybe by a factor of 10 or 20 simply by using these techniques. Okay, so if you need fast, a high timing accuracy, look for devices that have a serializer or deserializer built in to make a lot of different pulses that here I've drawn in there. Okay, say you have input lines that correspond to these pulses, so and then you serialize the input of these 16 lines, and then at the next time slot, you serialize the rest, and in this way you can get these things much faster. But this is sort of like a simpler technique, and we can just play with them with some cables. I'm not sure whether I just set something up so you can maybe you can see this in a short while if I get the screen working here. So that's a cheap and dirty way of making short pulses and adjustable pulses. The other trick you should probably be aware of is, now this gives you just the envelope of an electrical signal, and how can you use to modulate, say, a radio frequency signal that you would need for your acousto-optic modulator. Okay, so whenever you have a pulse, then you want to modulate often not directly a phase modulator, but a radio frequency. Okay, so that's a typical scenario you have, modulating RF frequencies or signals. And that could be, for example, you want to drive hyperfine transitions in an NMR scenario. Okay, there the energy levels are tens to hundreds of megahertz. Okay, so the connecting fields that transfer population from one state to the other are on the order of some radio frequency signals. Or for these acousto-optic modulators, you need to create a sound wave that scatters the light off. Okay, this is 10 to maybe 1,000 megahertz is a typical range. How do you go about that practically? Okay, one way is you get if you have low enough frequencies, you can do this these days with a direct synthesizer. Okay, direct synthesizer does something like that here. Okay, it has a time discrete way, and it just generates the sine wave or an arbitrary wave font, what you want to have. Okay, so in a time discrete manner. Okay, and tries to synthesize a sine wave. Okay, with time discrete samplings of it. Okay, so this would be a synthesizer or a direct synthesizer. Okay, and you can either make sine waves and start and stop those sine waves as you wish with a resolution of your synthesizer. Okay, that's typically on the order of 1 nanosecond time resolution. So you would find it a bit difficult to get to higher frequencies. Okay. The other trick is you have sort of like a constant source and modulate the radio frequency signal. Okay, so the same thing you can do with light field. You can also do for a microwave field. Use RF modulators. Okay, and you can sort of like look up radio frequency equipment, and they sell these things to you. Okay, so you have your radio frequency input signal. Okay, and this basically multiplies an electrical signal with your pulse waveform. Okay. This is called modulator, or you can also use, since this is just a multiplication, okay, you would find that a normal mixer works, okay? Can also work. Anything that multiplies one field with another field, okay, and that's typically what mixers do. We saw this in the homodyne or heterodyne, I hope. Oh, maybe we didn't see it. Okay, I forgot whether we covered this. A radio frequency mixer makes for a nice modulator. Okay. some are better than others, so you need to maybe play around with it. But if you need to quickly find some way of modulating a particular radio frequency with a given envelope, try a mixer, okay? And if things go right, I could just show you how this typically works. Yeah, what else is there to take care of? Okay, one thing, okay, if you work with radio frequencies, just one thing to keep in mind, okay, what you would like to see for your Rabi pulse would be an oscillation that looks like that and then stops again, okay? So if you look at the spectral composition of this particular pulse, okay, there are two time scales. One is the overall time, and one is the oscillation period, okay? So if you look at the spectral distribution of this thing, okay, you would have an F0. If you like, F0 would be 1 over this the oscillation period here, okay? So you would get a contribution which is called a carrier, okay? And if you have probably something at minus as well, minus F0. And you would get a contribution that's due to this envelope, okay? And the envelope, in this case here, is just a rectangular function, okay? And the Fourier transform of a rectangle gives a sinc function, okay? So you would get sort of like an envelope for this pulse here. It looks something like that, and on the negative side, something like that as well, okay? So that width here is essentially given by 1 over this time, if this is the overall time of the pulse. Maybe a factor of 2 or so of. Okay, so this is sinc function. Now, why am I drawing this? If you have any frequency-dependent components in your path, okay, that have different amplitudes from this part or that part of the spectrum for this pulse, you may just deform your pulse. Okay, so and that can easily hit you in a practical system when you have, say, working at the frequency of 200 megahertz as a common AOM frequency, and there's a narrowband filter somewhere that suppresses everything outside 200 megahertz plus minus 20 megahertz or so. Okay, then you can easily cut away parts of that frequency spectrum that would make you a nice pulse. Okay. Sometimes you find this also for some of these synthesizers. The way they generate these sine waves or whatever they generate, they sometimes have filter. I mean, they sample the wavefront they want to generate with a particular rate. Okay, and in order to make out of the sampled version a really nice sine wave, there's a filter that removes high frequency parts. Okay, and that filter, leaves all the low frequencies passing through, and the high frequencies get suppressed. Now you can't do this particularly, infinitely sharp, okay? Or you can do it, but if you do this, then signals that happen near that boundary get a very long delay. Okay, so if you use a synthesizer to make a particular wavefront, check out carefully whether you actually get what you want to see, because you may not be aware that there are funny filters in the system that make sine waves look nice, okay, on average, okay, but once you have a pulse sequence, then the wavefront you get may not look anything like that, but it may just be something like that, okay, and then take forever to ring down, simply because you have a filter that cuts off a particular frequency part. Okay, so this can be quite tricky. So one thing to do in a practical scenario, always check whether whatever you get out of your system looks like what you think it should look like. That's especially if you have short pulses or times where you get your filters in the way of something. I guess this is probably most of the stuff that I wanted to practically cover. I don't think it makes too much sense to go into the detail how to make such pulse sequences, because it's really just a programming exercise. Okay, you can do it yourself, or you buy these systems, or you get something that makes it. I guess I mentioned the typical ways of making wavefronts is, generate the envelope and multiply it with a modulator or mixer. If your envelope generator is too slow, play with tricks like that. Okay, that typically works. One thing I should probably say is I pretend that the pulses that come out here have the right amplitude that they can be digested by your modulator. That's typically not the case. So these digital pulses, they have a particular amplitude of 3 volt or 3.3 volt or 5 volt or whatever you have, okay, or 1.8 volt or -1 volt, depending on the logic you use, and you often need a particular amplifier to bring it to the amplitude that is required by your modulator. So that's then a bit of a tricky part, but this is so specific that I probably don't want to cover it in this lecture here, unless you have a specific question. So it's easy to make such a waveform with any of the digital gadgets that are around these days. Not every gadget would allow you to adjust the amplitude. That's okay. Any questions so far? I brought this toy along if you want to see how this delay trick works, if you haven't seen it yet, or how a mixer works. That's actually also funny. You use just a normal mixer and modulate the signal. It happens that the mixer I got is not particularly well suited. Okay, so you see the coarse gist, but I'm not even sure why I want to show it. It's you would like to see something like that, okay, and what you see is, what you would see is something like that. So it doesn't switch off completely. Okay, this is also something to keep in mind. These modulators, they may not switch off well enough. Okay, which means sometimes you have to have more than one in a series to make it really quiet out there, or use even different switching techniques to really kill off a light field. That is a common problem, because for these modulators we saw, okay, things to remember, okay. Okay, modulators are not perfect, okay. Which means when you think you switch them off, there's still residual transmission through it, okay. That can be detrimental if you want to have a period of time where you do a pi pulse here, okay, pi pulse here, and it needs to be absolutely dark there, okay, and this period here should be maybe on a few nanoseconds, okay, and you want to have it dark for a few milliseconds, okay, and that means that the Rabi frequency needs to be lowered by 6 orders of magnitude. That means that the amplitude of your light beam needs to be lowered by 6 orders of magnitude. Okay, and that's very hard to do with components like these mixers or modulators. So often you need to have two type of switches. One you use to shape the envelope on a short time scale, and another switch like a shutter or a acousto-optic modulator or something you can completely switch off. To cut off the light field way outside this pulse. And that's tricky. So most of the time when experiments require something like that, the hard part is to switch it off completely. Okay? So you have typically a sequence of modulators to really kill it down. That's one thing to keep in mind that one easily oversees. That's also where it happens. It helps to use radio frequencies to drive an acousto-optic modulator, for example, because you can change the frequency. Okay, so you can when the thing is on, you have a particular frequency, and when you want to have it off, you not only kill the amplitude that you may have to do with something like that, and that's not perfect. But you just move the frequency somewhere else. And And then you may be so far off resonant that the effective Rabi frequency is extremely small. Okay, so these are tricks to make sure that the imperfect modulators don't make your life troublesome. But this is getting extremely technical, so I'm not sure whether it makes sense to do this in a lecture style thing, or you just have to play with it yourself. Then when you start to see such things, and then you will realize that that all these ugly problems that pop up. Any questions? I set this up, but I don't think you will see more than what you see here on the whiteboard. So you can see a bad mixer. That's that's. Are you reasonably familiar with playing with cables and echoes in cables? Some of you have been in the previous module, others have not. So if you want, we can go through a few aspects of using transmission lines to play with pulses. Simply because let's give you an order of magnitude. I brought you some cables along. Okay, these are all normal waveguides. That's what we use typically for digital signals, but you may use something else. This is a short coaxial cable. It acts like a waveguide, and the time is like 20 centimeters long. It takes about 1 nanosecond, for a signal to travel through this cable. Okay, speed of light in this thing is 2/3 of the speed of light, because I think it's polyethylene insulator. So 20 centimeters correspond to a nanosecond. This is a cable. Well, I don't know how long that is. Looks like 50 cent, half a meter, something like that. Maybe half a meter. It's maybe 2.5 nanoseconds or something like that. So the time difference from here to here is that doesn't make sense. Anyway, but you get the idea that these pulse lengths you're talking about require you to think carefully how long can you make your cables. Okay, and it becomes a bit important to carefully think how to design your electronics to make sure that you match all the pulses hitting at some point your quantum system. There's also things that you should not forget in the lab, that whenever you transmit signals to these cables have well-defined impedances, meaning the ratio between the localized current and the voltage of this thing traveling along a cable are fixed. So this is when you say these cables, for example, have an impedance of 50 ohm. That means the ratio of the voltage and the current of a particular form going through this thing is just these 50 ohm. Okay. Also, most of the coaxial cables that you work with have an impedance of 50 ohm. And that makes it a bit difficult to get some of the digital signals through them. Which means like 3.3 volt signals or 5 volt signals getting through such a cable. You can work this out if you have a 5 volt signal from your standard TTL or CMOS device, and you would like to drive a 5 volt signal into a 50 ohm cable. You will need a current of 100 milliamps. Okay, which means just in order to get a simple signal from A to B, you need to send a power of about half a watt. Okay, just to switch something on and off, and that's typically a power that is larger than what you can get out of the digital circuitry that's around. So you need to think of how do you bring your signals from A to B. Okay, you can do this with coaxial cables. They have well-defined propagation properties. You can use twisted cables. That's what your Ethernet cable does, or your USB cable, or your plain old telephone cable, twisted pair things. Okay, they have an impedance of typically 100 ohm, plus minus something. Okay, so it's still not so easy to transfer signals from A to B through such cables. Yeah, so a lot of work when you work with fast pulses, goes into making sure that you can bring your signal from A to B, in a way that doesn't disturb pulses. One thing that maybe also worth noting is there's different types of coaxial cables. I'm not sure I have a long one here. Okay, so the cables I show here are quite thin, simply because then you get more cables per area of your device on it. If you get the standard BNC cables, they're a bit thicker, then you can imagine that the whole thing gets larger and more messy. So you need to make a compromise there. So physical size of cables is a matter. This is an example of this HDMI cable. I guess that has a bunch of waveguides in it that are twisted pair cables. So that typically runs on 100 ohm lines. I think they have 6 or 7 of these twisted pair things in such a cable. What else is there? This VGA connection has, I have no idea what that is, whether it's even well defined. Probably also around 100 ohm, but I simply don't know. So whenever you work with fast signals over lab scale equipment, this is probably your most expensive concern, working with these cables. But I'm not sure whether this justifies a lecture. It's something you see easier if one works on it practically. I'm not sure it's worth switching on this oscilloscope really. We can do it, but maybe just easier if people ask questions. Yeah. Or start focusing on projects. Because time is at some point running out. Okay. Should we make tomorrow a project discussion day? So everybody prepares questions and whatever is going on. If you want me to do something or get you materials, let me know. But please start working on your projects and start documenting as well. Okay, on this wiki thing, because at the end I know documentation is something that is always painful and there's never enough documentation. But the idea is that you also learn how to document your small project somehow in a way that someone else can understand it. And this will be the way I need to assess. Yeah, I need to assess somehow how you do in this course. And easiest way is I watch this thing and come up with a number between 0 and 100 or something like that. So this would be the assessment component of this course. So don't do it in the last minute, because then it's a bit of a rush or something like that. Okay. I think that's it for today. Thanks. Just switch off this guy.